Thank you for the introduction, and thank you for the opportunity to give this talk to the organizers, I think maybe Christian in this case. And yeah, so I would like to talk about some joint work. It's actually a collection of a few papers from the last 5 years with mainly Daniel Burgert, Paolo Facchi, and Christian Arns was involved in one of them as well. So, so this fits sort of into the part quantum information. So this workshop has like these 3 pillars. I think this fits into quantum information, but it's still a little bit disconnected from what we've heard in most other talks. And so I will try to keep it simple and explain everything that we need. So in particular, I will have to explain these words. I guess dynamical decoupling is quite unfamiliar to most people, and open quantum systems, I also give a very rough, like conceptual idea of what I mean by this, and then how they connect and why we need them. So first of all, why do we, what has it got to do with quantum information? So a quantum computer is often modeled as an open quantum system. So you have the quantum computer, and it sort of interacts with the environment, and that makes it an open quantum system. And so in order to understand that and to control that, one then uses this method of dynamical decoupling. So that's it in a nutshell. I'm going to say a few more words now. So maybe we start as follows. So we have our, say, an internal system, which is modeled by a Hilbert space, say with a unital, completely positive time evolution on that Hilbert space, so a family of quantum channels. And so that's my one system that I would like to study, for example, my quantum computer. And then we have an environment, which is also a quantum system, and we model that by another Hilbert space, and there might be some time evolution here as well. And we have states on both, or a combined state on the combined system. So we have something which is bipartite, similar as in the previous talk, but there's no entanglement here. There could be, but that's quite irrelevant for this setup. And so the environment, okay, is actually, let's make it bigger because it's big. It's very big. So this could be the whole universe, apart from the internal system. And then the point is that we've got some interaction between these two systems. And in the entangled case, you want some connection between these two systems. But here we want exactly the opposite. We want the system to be isolated. So imagine you have a quantum computer, you prepare some state, you put some information into that computer, and you want it to be saved and over time. You don't want it to get lost. You only want to apply certain specific operations on that system, but nothing else should change the state. Only your specified quantum operations should change the state. But reality is not like that. So if you look at quantum computers, so 2 weeks ago we had people from industry. We had a chat with them about quantum computers. So they use them, they build them, and with some of them. And that's a big problem. So the problem is, let me write it down here, as the word decoherence. I'm not going to really define this, but let's just work with decoherence as sort of loss of information over time caused by this interaction. Okay, so we have some information here, but there is some interaction. So interaction is, say, a unitary time evolution of the total thing that you build. So, yeah, the total thing. And that leads to information being lost. You could measure that, for example, if you compute something like the entropy of a state that you prepare on H0, and you study that state over time, then the entropy will increase. So that's a property of completely positive maps, that if you compute, say, the von Neumann entropy, then that will increase in general. If you have unitary time evolution here, then everything remains preserved, but in general that could increase. And that's something that we do not want. And so the idea is to apply quantum control operations to this, well, basically to this internal system in some way that eliminates this interaction approximately. We'll never be able to switch it off completely, but one can try to switch it off or reduce it approximately so that at least you can carry out operations, computations, and have your information saved for, say, a few seconds, right? That's already a lot for a quantum computer. Imagine you keep information on your laptop but just for 2 seconds safe, and then it's lost. So it's pretty bad. But for quantum computing, that seems to be already great progress. Okay, so that is sort of the basic motivation. So let me write down, we need something else. So we want to look at some of the maths in here, and so not too much into the physics. So what we need, are a few definitions. So the first definition is the following. So given your internal system, so that should be a Hilbert space with some UCP time evolution, one parameter family, do the following. So a strongly continuous autonomous unitary dilation. So that's my definition. So I can, for the rest of the talk, just use the word dilation, but that's what we mean, is given by a triple HE omega E, and here we have a one strongly continuous one parameter semigroup, such that U T is a strongly continuous one parameter group on this joint Hilbert space. And I will denote this by H hat. So we take the tensor product of the two. So the tensor product of this one times this one. That's the total Hilbert space of the combined system. And on this I want like this one parameter unitary group. And omega E should be a state on this Hilbert space here. Okay, such that this, and the important thing is the following. So maybe this definition. So let's work with the following picture. Picture is always nice to visualize. So we have our internal system with a time evolution in here, and dilation means I want to sort of embed this into a bigger system. So, well, this is just H hat, and that's the same as B of HE tensor B of H0. Okay. Then on here, I would like to use this unitary time evolution. So we have an automorphism here. And then project this back down on here using sort of, not the partial trace, but using this fixed state that we have. And here, the embedding that we use is taking just the identity on HE. So the unit element here times the identity map. Okay, so the whole thing should commute. That's what we mean by unitary dilation. So maybe you haven't seen this before, but everyone will have seen the Steinspring dilation before. So if you have a single UCP map, you can apply the Steinspring dilation, and you get out of that a star homomorphism. Now here, this is a bit more restrictive. First of all, we don't just want a star homomorphism, we want to get an automorphism, so that is more restrictive. However, if you have a star homomorphism, you can carry out another dilation to a higher level and get a star automorphism. So that's the first generalization, or not generalization, specification. And the second restriction is that we want actually this whole thing to work for all t in a compatible manner. So that means if you compose phi t and phi s, that's the same as composing it here. So you cannot just do it for individual maps, you have to do it for the whole semi-group. And that's why we need this. So the question is, do these things exist? First question. And I want to say this now. Maybe not now. Okay. Now I want. Yeah, maybe I say that later then. So that's the first definition, and maybe so the interpretation of this would be that if you have just your internal system here, and this time evolution, then that always arises in such a way from a reversible, so this unitary time evolution. You see, a UCP map cannot be inverted in general, but an automorphism can be inverted. So this way, this upper line is a bit nicer, and so that tells us that the time evolution on the whole thing should be somehow reversible, and that gives me the irreversible time evolution on the smaller system. Okay, so in that way, H0 will often called an open quantum system. Because it's not isolated, so there's some interaction with the environment, and the whole thing together, H hat, would then be called a closed quantum system. Okay, so that's what one physically sort of sees behind this, that such an irreversible time evolution should come from something reversible. Okay, maybe let's say the thing, what we know mathematically. So, put it like that, such a dilation always exists. Okay, so in this context, such a dilation always exists. So this is not new. So this was shown like 40 years ago by, first I think Evans Lewis, in the case where this time evolution is uniformly, so norm continuous, not just a strongly continuous, but norm continuous. And in that case, these could be arbitrary von Neumann algebras. That's what they did. Later on, shortly after that, using quantum stochastic calculus, it was then shown in this case, but with strongly continuous semigroups. So these are then called quantum Markov semigroups. Some people are very familiar with these. So in that case, using this Hudson-Pater-Serati quantum stochastic calculus, one can construct, and the dilation due to Avison, one can then construct such an irreversible dilation in this case. So these things always exist. In particular, in our case, we will work with finite dimensional H0. HE will always have to be highly infinite dimensional, but H0, if that's finite dimensional, then all these theorems apply, and we can always get such a dilation. What we did in our work, because that was needed for dynamical decoupling methods, is we've created another dilation, and that also works in the case where phi t is not a semi-group, but just like a one-parameter family that is analytic. So there are different types or different results, but one can always use such a dilation, and you also see that it is not unique at all. So there are plenty of dilations that fulfill this condition here. Okay, so that's what we have so far, and then maybe wanted to introduce some control operations. So definition. A dynamical decoupling set for H0 is given by a finite subgroup of unitary elements on H0 such that if I average over them, then that should be multiple of the unit element. And you see we require a finite dimension, so maybe let's put that right here, maybe henceforth H0 finite dimensional. So you might not like that, but physicists are happy with that because the quantum computer is finite. So you can work with this. You can think about how to generalize this. Mathematically, that's of course interesting, but then you would have to find a different definition here. Quick question?
Yeah, so the trace there is the normalized or unnormalized trace?
So this factor normalizes.
Yeah, okay, but the trace itself, even though it's small.
Yeah, the trace itself is like the standard trace, and I use this in order to normalize it. Okay? So here we have this as normalization. Okay. Right. Next thing, a decoupling cycle is like a finite sequence. Finite sequence, V1, reaching every element in V, same number of times. Okay, so that's my coupling cycle, and it has length n, so n is a multiple of the size of V. Okay, it's not a particularly difficult definition, and one can always get such a decoupling set. Just have essentially a subgroup that acts irreducibly on H0, so you can always find such a subgroup. So as an easy example, if H0 is C2, then, for example, use the Pauli matrices. So you have the three Pauli matrices. And that, okay, that's not a group, but in the adjoint representation, it will act like a group. That's sufficient. Okay? And that's the most important quantum system that exists. So that's fine. Qubits are done. Right, so now what do we do with this idea of construction? So how shall we apply these control operations? So well, you see that this V will act on H0 essentially, and that's also what we have to do. So we cannot control the environment. We can't do anything about the environment. We can only access the system itself. And still we would like to so we can only work on this white circle, but still we want to affect the red one, so sort of cut them off here. Okay, so that's the goal. And so how do we do this? So now consider the following. Let's call it perturbed evolution on H hat. Perturbed evolution on H hat. So what do we do? So we define the following. So fix t somewhere here, and then for every natural number, we then define the following thing. We apply these operations here in between the original time evolution of the system. So I think it's again nice to see a picture. So here we have time 0. Here we have time t that we fixed. And then let's say here we have time t over little n. And this interval we split into capital N steps. So here and so on. And here we put time t over little n, capital N, 2t over little n, capital N, 3t, and so on. So the time evolution that we have over this interval is then u over. Okay, so this u hat is the one. Maybe we should put it here. Hat. Okay, this is this time evolution on the joint system, and so this is a one-parameter group u hat, and so it evolves for time t over nn, and then what we do here we apply the following correction operation. V1 star Vn. Then here we apply the operation V2 star V1. Then we let it evolve with this natural free evolution. And then we apply another correction operation and so on. Okay, so here we get again V1 star Vn and so on. All right, so you can write that out as follows. So since this is a one-parameter group, it has a generator, which is, we call the Hamiltonian, so a self-adjoint element on H hat, on this joint Hilbert space. So I can write it as e to the it in H. And so we have this product. And the whole thing to the power of. Okay, and so you can simply rewrite that as follows. So we pull the Vn up into the exponent. So these are some very basic manipulations, but I'm doing them because it nicely shows what's going on here. Okay, and then in the next step, so we formally compute like the series expansion, Taylor expansion of each of these exponentials. And so we can write this as, you have the sum, first order, so we take the expansion in the order of little n. So vk, h, vk star, plus order 1 over n. Okay, so here we sum over all the k's. And now we use this property here. Okay, so this property says that if I sum over all these vk's, I reach all of them the same number of times. So this is essentially averaging over my subgroup V. And that means this is just a multiple of, can I write this? Let's write it here. So this is equal to 1 plus I t, and here we have B, tensor unit plus order 1 over n. Okay, so on the system part, I just get a multiple of the unit element due to this very simple condition here. Okay, on the environment, I can still get some time evolution, but on the system, it's just a multiple of the unit. And so that means that essentially the system does no longer evolve. Okay, approximately, because we still have all the remaining terms in the power series. So we must somehow show that all the remaining terms do no longer contribute. So we're essentially interested now in the case where little n goes to infinity. So we squeeze more and more cycles within this fixed time interval, more and more, and we look at the limit where n tends to infinity. So the question is, does this limit exist, and what do we get then? Okay, so imagine the simple case where HE were finite dimensional, then our Hamiltonian has to be a bounded operator, and then this formal calculus is sufficient and everything is fine. So that was the case in the original paper. So this idea, maybe I should say, I didn't say that. Okay. The idea, so this goes back to a group of physicists from around 2005, and that was sorted. But so since we have to do with unbounded operators H, the situation is actually not sorted at all, because all kinds of problems can now arise. So we don't know whether this limit, when n goes to infinity, actually exists. Okay, and so that's what our work was then about. So the question does this limit actually exist? So does this all make sense? So we need another definition. So we say, so in the above situation with all the, in the above situation, so with the fixed quantum system, the fixed dilation and a fixed decoupling set and cycle and everything fixed. So we say in this situation, say dynamical decoupling works. So if for every state on my system, I get that, so we take the product state on the total system, so we have the state on the environment, which is fixed from the dilation, and here I pick my arbitrary state. I compose that with this perturbed time evolution. And then I take the norm, so basically operator norm on the state, and this should go to 0. Okay, so that would mean that if I put in an arbitrary state in here at the beginning, and then I switch on my system and I apply these correction operations very, very fast, and faster and faster, and then this will go to 0. Okay, I can actually show how fast, or determine how fast to compute them. So that's where the physicist will be happy, because you can give some error bounds here. Whenever it works, one can actually then compute these error bounds using some information about the system Hamiltonian, and show that they, so maybe put that here.
problem. Do you want T fixed or?
Yes, so I said, where did I say that? Fix T.
Oh, okay.
Okay, but in the end I want this to work for every T, but so for this, sorry. So here, no, it shouldn't be fixed, sorry. Here we say, yes, here we say, so uniformly for T in compact intervals. So compact intervals in 0, infinity. Okay? So, but in order to define this, I fix T. Okay, remark, so when it works, then the error here goes approximately like 1 over n. So there's a constant that depends on the time and internal parameters, but not 1 over n, but not on the number of decoupling cycles. So by just squeezing in more and more correction operations, you can get the error as small as you like. Okay, so that's maybe, yeah, we can call it a theorem if you want. Call it a theorem, even if it's not really nicely written, but that's it. So the actual theorem that I wanted to write on now is the following. So yeah, the question is when does this limit exist? So when can we fulfill this condition here? And so one nice theorem that can be applied to many examples is the following. So we look at the Hamiltonian of the joint big system, and I conjugate this with all the v's. Okay, so I have a finite sum here, and if this one is essentially self-adjoint on the intersection of all these domains, which in particular need to be dense in the whole Hilbert space, and omega e is normal, then dynamical decoupling works. Okay, so that's the first result one can show, and then there are plenty of models where one can prove that this condition is actually fulfilled. So models that are used also as like in physics, which is quite nice. And so another result is the following. So given my small internal system, so this is the internal system of interest, then there are dilations. Sorry, the system with fixed decoupling set and decoupling cycle. So I have my system here, and I have the set V that's given by this definition. But I would like to look at the dilations. I already mentioned there are several dilations. So we can ask the question, do these dilations behave differently? And so the result here is the following. There are dilations given coupling set. There are dilations such that dynamical decoupling works, and other dilations such that dynamical decoupling does not work. So this is a nice theorem because it tells us something, but it's not so nice because actually we would like it to work for every dilation, because typically we can only access the system and sometimes the environment is not known. So if I don't know anything about the environment, then I cannot tell a priori whether it will work or not. That's quite surprising, because if you just look at systems, so all these environments give rise to the same dynamics here. There's no way of distinguishing the dynamics here, and still for some of them you are able to switch this off, and for others you aren't. And you can just test it. So as an experimenter, you could just test it, but you cannot predict it. If you know something about the environment, so for example here, you have to know the Hamiltonian, then you can say much more. Okay, so that is, in many instances one does know more about the environment, so one is not completely lost, but we would have hoped this to always work, which is not the case, unfortunately. So that's one theorem, and then maybe we don't have much time, 30 seconds. So maybe one final theorem that says that, so something that people often complain to us is that it's unphysical to have these instantaneous correction operations, because you would require infinite energy. I think that doesn't concern us, it doesn't bother us, but in the lab they are bothered by that. And so they say typically you will have to spread that out over a certain time interval. So one can do the following. Suppose one spreads this out with a parameter lambda. So instead of having an instantaneous interaction, one spreads it out over lambda, so that this gives you a unitary that is implemented by Hamiltonian dynamics. And so the statement is as follows. If correction operations applied smoothly instead of instantaneously, then further conditions are required. So again, there are models where one naturally fulfills them, but there are also models where they are not always fulfilled. However, are required in order for this to work. However, in the limit where this parameter lambda, which is greater than 0, so when I let this go to 0, goes to 0, it will always work, provided the instantaneous case works. Instantaneous case worked. So that means this idealized setting with instantaneous operations is a good approximation of the actual physical setup. So that's why we've proved this, and so that's also nice result. Okay, I think that's in a summary, we looked at this mathematical description of this correction operations that are actually used in quantum computers, and try to find like error bounds and criteria for when it works. And so I presented some of them here, and now I have to stop.
Do we have one quick question for Robin?
So, suppose you go to your theorem, you find one relation for which it works, for which it does not work. But suppose I can find a different decoupling set that works for the other one. Can I combine the two to find the probably bigger decoupling set that works for both?
I think you can actually construct a dilation that won't work for any decoupling set. You don't actually have to change the dilation, and the other way around. So we don't I specified it here, but we don't actually need to specify this decoupling set. So anything that will fulfill this condition with this fixed system Hilbert space will give the same result. So there will be dilations which cannot be decoupled at all, and others which always work.
And then we can continue the discussion break. Yeah.
Thank you.